This is lecture 15. I have no idea what does this correspond in terms of standard front teaching hours. I completely lost track of that. Anyway, that's a weird year, isn't it? We continue our journey in transition path theory, and hopefully today we'll try to make sense through examples of why this is all useful. In order to do that, let's review what we've done so far. Besides defining what is a transition path ensemble, we also introduced three main stochastic descriptors, so we called it, which are the main theoretical ingredients that enter the description of reactive processes. And we listed them to be the committer function or the forward committer function, the backward committer function being trivially related to the forward for Markovian dynamics, the transition path density, and the transition path current. And we began not only giving definition of these three stochastic descriptors, but also trying to establish a relationship between these three stochastic descriptors and the fundamental ingredients that enter in the physics, where the physics is channeled in, which is essentially the diffusion coefficient, the potential energy function, and the temperature or inverse temperature, kT. So in other words, how can we calculate these three stochastic descriptors given the model? And in the last lecture, we concentrated on this. And we showed through some sort of not completely trivial calculation that Q plus obeys a specific partial differential equation, which is the adjoint of the Fokker-Planck operator set to 0. So in other words, Q plus is a left zero mode of the Fokker-Planck operator, satisfying specific boundary condition. Where the adjoint of the Fokker-Planck operator is basically this operator. That's what this means. Now, one thing that I think should be sort of noticed is that the role of boundary condition is essential in determining the structure of Q+. In fact, in one of the previous lectures, we noted that while the lowest right eigenmode of the Fokker-Planck operator was Boltzmann, the lowest left eigenmode of the Fokker-Planck operator was unity. Remember? And the way we did that is that we could construct left eigenvalues operators in general by multiplying up to a normalization constant that I don't quite remember now. I think it was root of 2, but never mind. By taking, yeah, I think it was root of z e to the beta half u of x, the Hermitian eigenmodes, and in particular, since the Hermitian eigenmode for the ground state is the root of Boltzmann, then clearly L naught was 1. So the left zero mode is essentially the right zero mode of the adjoint operator, right? And clearly this is a solution of the right zero mode of the adjoint equation, because let me remind you, the adjoint equation has a double derivative, negative, a force field times a single derivative. So if I add this to any constant here, this is obviously 0. However, in general, the commuter is not a constant, because if the commuter was a constant, it means that no matter where you start in between the reactant and the product, you have the same probability to make it to one side or the other side of the reaction. And that's not what happens. It's not what happens because the boundary condition completely changes the structure of the solution of a PDE. Now, this is somewhat a trivial statement for those who have seen many PDEs in their life, and it should be sort of familiar after having seen electrostatics, as we were saying last time, because the whole plethora of possible electrostatic fields that can exist in the world, they are the solution of the same Poisson equation, well, with different sources, maybe, but with different boundary conditions. So the commuter is actually doing something quite interesting. And it is instructive to look at a commuter in 1D first. Because if you look at a commuter in 1D, well, that's something quite interesting seems to be occurring. And it's the following. Well, first of all, the commuter is quite good in finding what is called the transition state. Now, if I were to sort of explain what a commuter means in a simple model, well, typically you have to define a basin for the reactant and the product, and a natural way to define it is to say, I don't know, maybe this is kT. The energy is equal, this energy is equal to kT, or 1/2 kT. Yeah, can be sort of flexible in defining your basin. Suppose this is twice the thermal energy, kT. So that, 95% of the time within the valley, since this is since the ground state solution of the harmonic oscillator is a Gaussian, choosing this to be twice the thermal energy is basically telling you that you're satisfying 2 sigma confidence that you're within there. This is, of course, my product. And this is the transition region. So if I were to look at the trajectory in configuration space, I would say like something like this: thermal oscillation in reactant, and so on and so forth. This part leaves the react, so now I'm going to draw the border of the reactant and the border of the product. Now you clearly see that sometimes you leave the border of the reactant, but you re-enter the reactant before landing into the product. But occasionally you don't. You land into the product before entering the reactant. So that means that this would be a member of the transition path ensemble, while everything else would not. In addition, anytime you reach a point in which Q plus is equal 1/2, then you have 50% probability to land to the right or to the left. Now, it is intuitive to see where this point is on this plane, right? It is clearly here, or exponentially close to the barrier top. if you're at the barrier top, really, you throw a coin and you decide where to go. However, it's important to emphasize that a committer is not a local function. It's a global function because boundary conditions are non-local concepts. Differential equations are, of course, local. You can ask your field to locally satisfy a differential equation, but the boundary conditions are global, so you need to know all of space before you can determine Q plus. So that's why that's why I'm saying that the Q plus 1/2 is exponentially close to the barrier top, but it's not at the barrier top because it depends very much it depends slightly on where I put the border here, or how far the borders are, and all of that. So I guess I have some examples, numerical examples, and I might play with numerical examples in the next lecture, just as we did for the solutions of the Fokker-Planck equation. But we can already see how things actually change qualitatively for a committer. So normally, let's consider a barrier first with a single top, a single transition state. Now, typically, the committer, if I were to plot it, the committer is only defined from here to here because here is 0. Here is 1. And there is some kind of a behavior like this, and if I were to draw where the 1/2 is roughly speaking here. That's my committer. It is more interesting to look at a committer when you have more than one barrier. So for instance, you're like this. Now, you see, if this is a thermally activated basin, points within the basins are exponentially close to one another. Which means that basically any point here has up to exponentially small correction, the same probability of making it close. When I mean exponentially close, I mean in kinetics. And therefore in probability of making to the right and to the left. Why? Because they fast propagate from here to here on a very short time basis. Diffusion here is taking care of them. So basically any point in this red basin has almost the same chances to make it to the right than to make it to the left.